Hey everybody, this is our video solution to problem 3 from quiz 14, spring 2023, Math 302 at Cal State Fullerton. So in this problem, we are given the group S₄, the group of permutations on the set 1, 2, 3, 4, and we are then given 4 subsets. So we see that down here, A, B, C, and D, there's going to be 4 subsets, and we would like to know whether or not these are subgroups of G. So one thing that is maybe the fastest thing to look for is the cardinality of the subset versus the cardinality of the whole group, because then we can employ Lagrange's theorem. So why don't we just write that down quickly and see if that maybe resolves something very quick, like really fast. So the size of the group, size of S₄, is just 4 factorial. That's the total number of ways to permute 4 objects. So this is 24. So what we would be looking for in any subset that wanted to be a subgroup is something whose cardinality divides 24. So let's look at the first one. This has 1, 2, 3, 4 elements in it. Yeah, that 4 does divide 24, so we can't rule it out based on Lagrange's theorem. Let's see this next one. 2 elements. Nope, 2 does divide 24. Third one, a subset of cardinality 5. Well, it says something, something. I don't care. Cardinality 5. 5 does not divide 24. 5 does not divide 24. And so, by Lagrange's theorem, which tells us that the cardinality of any subgroup must divide the cardinality of the whole group, we know that in C, we do not get a subgroup. Okay, and the last one, 1, 2, 3, 4. Yep, okay, that also does divide 24. So this is the only one where we can use Lagrange's theorem. Okay, so the next thing I would look for if I was trying to rule something out from being a subgroup is I would check to see if there's an identity. All right, so let's see. In the first one, yep, there it is. We have the identity element. The second one, oh, look at that, no identity. So we can immediately say E is not in the subset. And so this implies not a subgroup. Okay, we've already established C is not a subgroup. Let's look at D. Oh, there it is. Yep, we have the identity. All right, well, what's next? Next thing I would want to look for are inverses. Can I immediately find all the inverses? All right, I don't have to worry about E. Now each of these is a transposition. Well, transpositions are their own inverses. So yep, we have all the inverses here. These are double transpositions, right? So a transposition by a disjoint transposition. Those are also their own inverses. So yep, look at that. Not going to rule anything out based on inverses. Okay, finally, I want to make sure that each of these subsets is closed under products. So let's see here. Certainly multiplying by the identity won't do anything, but what if I take 1, 2 and say 1, 3, and I compose them? So this would give me 1, 3, 2, right? We check 1. 1 goes to 3, and then 3 is fixed, so 1 goes to 3. 3 goes to 1, 1 goes to 2, so 3 goes to 2, and then 2 goes, well, it's fixed here, and then 2 goes to 1. All right, but this is not in the subset, right? So this is not in the subset. And so the subset is not closed under products, and this tells you that it is not a subgroup. All right. Hey, there was a hint that only one of them is a subgroup, and we've just ruled out 3, so we know this last one better be a subgroup. All right, well, that means we got to make sure that it's closed under products. So again, we just need to essentially make sure if we take any 2 of these and multiply them together, we stay in that set. And in fact, you notice these 3 double transpositions, you can kind of get ones from the others just by permuting the numbers around. So we actually only really need to check any 2 of them, right? So I'm going to take, say, the first 2. 1, 2, 3, 4, and let's compose that with 1, 3, 2, 4. All right, so let's see. 1 goes to 3, 3 goes to 4, 4 is fixed, so in total 1 goes to 4. 4 goes to 2, 2 is fixed, 2 is fixed, and then 2 goes to 1. 4 goes back to 1. All right, now let's check 2. No, we did, yeah, we haven't checked 2. Let's check 2. 2 goes to 4, 4 is fixed. 4 goes to 3, 3 is fixed. So 2 goes to 3. And of course, we really don't have to check 3 at this point because there's nowhere else for 3 to go but back to 2 because we only have 4 numbers and we're looking at bijections. But just for fun, 3 is fixed, 3 goes to 1, 1 is fixed, 1 goes to 2. Okay, sure enough. And 1, 4, 2, 3 is in here. All right. So again, if I just permute the numbers in here, right, like I'm just going to basically be swapping these around, you can see what happens. If I take 2 of these, I get the third as the product. And if I took 1, 2 with the 1, 4, those ones, I would get the 1, 3 version out. If I took 1, 3 with 1, 4, I'd get the 1, 2 version out. So you could check that piece by piece if you like, or make really a symmetry argument to show that all 3 of those products are going to be inside. And there's no other products that we need to check because we know that these are all invertible and they're their own inverses. So we don't have to multiply them by themselves anymore. So in fact, we do have a subgroup. Okay, everybody, we'll see you next time.